Welcome back to NE 630, nuclear reactor theory. So we will continue the same business that we were doing last time, which is the derivation of the point kinetic equation. Before I start, a couple of hints about the homework. Some of the students, they asked me about problem number 2, and they did not get the exact answer for the slowing down density. I think the majority of them, they were doing the mistake of integrating not over delta E double prime. So if you integrate over delta E double prime first, everything will be constant. So you will get it outside the integration. The second one is the last equation, and when you integrate e to the power of 3/2 e to the power of minus e over kt, some of the students asked about using numerical techniques or using the calculator or whatever without showing the answer. Yes, you can. So this function usually is called the gamma function, and the gamma function is defined as, if I remember correctly, gamma n is defined as from 0 to infinity, x to the power of, I think, n minus 1 e to the power of minus x dx. If I remember correctly, that this is the gamma function. And of course, you have a recurrence relation for gamma function. So I think gamma half, I think, was something like square root of pi over something. Maybe just I'm giving you a figure of what's going on. I do not remember the exact formula for gamma half, and maybe I am off by some number here. But you can use the Mathematica online engine to do the integration for you if you want. So let's now continue the same business that we were doing last time. Last time we showed that for a tightly coupled core, for example, we can separate neutronically tightly coupled core. So for a reactor core that is neutronically tightly coupled, we can write our equation 5r and t as equal to some spatial function psi of r and t multiplied by a function n of t multiplied by v. So this is some function of r multiplied by some function of t, and the function of t, it's a flux function, so we make it like Vn of t. And again, we can show also that the concentration as a function of c and t will have the same shape function for the concentration, because the number of delayed neutron precursors will be coming from the fission. So you expect that because they are coming from the fission, they will have the same shape for the flux inside the core. And this is also again multiplied by Ci as a function of t here. So psi of r, we call it a shape function that gives the shape of the flux inside the core. So if you apply this to the formula that we wrote last time, so for dc by dt will be now psi of r multiplied by dci of t by dt equal to beta I nu sigma fission multiplied by the flux, and the flux now is just psi of r multiplied by v multiplied by n of t minus lambda I multiplied by ci of t multiplied by psi of r. So if you look at here, this was just what? the continuity for the concentration of the delayed neutron precursors that we wrote last time. So now, did you see guys, that when we will convert or decompose the flux to those two functions, now this function is only a function of what? Of r, does not depend on t. And here is the same function of r, here is the same function of r. So all what you will do what? You will cancel this one, and you will have dc I as a function of t by dt equal to beta I nu sigma fission multiplied by what? Multiplied by velocity multiplied by what? N of t minus lambda I ci of t. Okay, guys? And there's VI here also. Or no, there is no VI here. Okay, so what's the second equation? Or we can still with this one. So this is just beta I multiplied by N of t, and I can make this divided by capital gamma minus lambda I ci of t. And what's capital gamma from here? What's capital gamma? So this is bi multiplied by ni. So you end up with what? Nu v sigma fission. So this is what? 1 over nu sigma fission multiplied by the velocity.
So is that the speed of the neutrons that are coming off?
This is the speed of the neutrons. It's a single energy equation because we average over everything. This is sigma fission nu, and you knew what's this? We defined this before.
That's the number of neutrons from a fission.
Yeah, but we define 1 over nu sigma v. So what's 1 over sigma? Lambda mean free path. Yes? Divided by what? Nu v.
That's just the time.
Yeah, so this is defined as the mean generation time between the birth of neutron and the subsequent absorption. Subsequent absorption leading to fission. So mean neutron lifetime or mean neutron generation time. So this is the first equation then. dci by dt is equal to this. How many equations do you have here? Huh? 6. 6 equations. Because we have 6 groups. Yes, guys? Now, what's the second equation that we have to write? What's the second equation, guys?
The flux with time.
Yeah, which is called what? Huh?
Continuity.
Nope. What the equation that we have been using for the rest of the semester. Last time, every time we solve this equation in a slab and here and there and diffusion. So the diffusion equation is just 1 over V d5 R and T by dt equal to what? D Nabla square phi minus sigma absorption phi plus the sources, and the sources I have one which is the fission prompt source, and the other one is what? The delayed source. Okay guys, so we will do exactly the same. 1 over V, and what's phi from over there is equal to what? Is equal to V multiplied by what? Psi of R multiplied by dN of T by dt equal to D Nabla square psi of R V multiplied by what? N of T minus sigma absorption psi of R N of T multiplied by V plus 1 minus beta nu sigma fission psi of R multiplied by N of T multiplied by V plus lambda I multiplied by C of T multiplied by psi of R. Can we cancel psi of R from both sides? How many will say yes? How many will say no? Why no?
Because you were summing that last term.
It does not depend on the summation is over I. Yeah, we cannot cancel because this is differentiation with respect to R, and this function is what? Is a function of R, so you cannot cancel it. Yes? So we have to do a trick so that we will be able to cancel it. What's the trick to use? The reactor equation is Nabla square phi plus B square phi equal to 0. This was the reactor equation. And B is what? We'll call it BG. This is the geometrical buckling. Yes? So if you substitute here, this will be what? Nabla square phi of R multiplied by V multiplied by N of what? N of T plus B square what? G multiplied by psi of R multiplied by what? V by N of T equal to 0. What term can I cancel from this equation? V, what else? N of T, I don't have any d by dt. So V N of T will be cancelled. V N of T will be cancelled. Then you can take this term to the other side of the equation and you will get a negative sign. So what's Nabla square psi of R? Negative B square G psi of R. So I can remove from here this, and I will put what? Negative D B square G psi of R. Now, can I cancel psi of R? Yes? I can cancel psi of R. Yes? So here is psi of R, does not depend on I. So I can take it. Here is psi of R. I can what? I can cancel it. Here is psi of R. I can cancel it. Here is psi of R. I can cancel it. Yes, guys? Okay? And here is psi of R. I can cancel it, and V will cancel with V. So somebody will has to help me in writing down what we have right now. So what we have in this term, dn by t equal to, what's the first term? Negative d b square g multiplied by what? N of t multiplied by the velocity, plus or minus sigma absorption multiplied by N of t multiplied by the velocity. Yes? Plus 1 minus beta multiplied by nu sigma fission multiplied by V multiplied by N of t, plus summation of lambda I Ci of t. Yes, guys? Guys, do you agree? So we have to do some tricks so that we'll be able to use this one. So I can expand this. I will multiply nu sigma fission V N of t multiplied by 1. Okay, guys? Then I will multiply it by negative b. So I will have what? Negative b plus nu sigma fission V N of t. I did not do anything, just I expanded. Okay, guys? Then I can take N of t multiplied by V multiplied by sigma absorption as a common factor from all terms except this term. So N of t V sigma absorption, I will take it from this term. So if you take from here N of t V and sigma absorption, you will end up with N sigma fission over sigma absorption. Am I right? Yes? Okay. And if I take it from this term, this will give me what? Beta nu sigma fission over sigma absorption. And if I take it from this term, will give me what? Guys, give me 1. And if I take it from this term, will give me what? D over sigma absorption multiplied by what? B square G all plus summation of lambda I Ci of t. What's this?
L square. 1 over.
What? Yes? So this is L square. Can I write this as negative 1 plus L square B square G? Yes? Yes, guys? And then can I write okay, guys, so this will be N of t multiplied by V sigma absorption. Then I will rearrange the terms here. So this will be nu sigma fission over sigma absorption minus 1 plus L square B square G minus B nu sigma fission over sigma absorption, all plus I equal to 1 to 6 lambda I Ci of t. I did not do anything except rearranging everything inside. Do you have any question, guys, so far? Guys, do you have any questions so far? So now, it will be equal to dn of t by dt equal to n of t multiplied by sigma absorption multiplied by v, all multiplied by this. If I go back here to this bracket here, okay guys, and I take 1 plus L square B square G as a common factor, I take it outside the bracket. So this will give me what? 1 plus L square B square G, and I will end up with what? Nu sigma what? Over sigma absorption divided by 1 plus L square what? B square G minus 1 minus nu sigma what? Fission over sigma what? Absorption multiplied by what? Beta plus the summation of lambda I Ci. So this will be N of t sigma absorption V. What's this?
K effective minus 1.
This is what? K what?
K infinity.
K infinity. And this is what?
Probability of non-leakage.
The non-leakage probability. So K infinity over the non-leakage multiplied by the non-leakage probability is K effective minus 1. So this would be 1 plus L square P square G multiplied by what? K effective. Yes. Minus what? Minus 1 minus nu sigma fission over sigma absorption multiplied by beta plus the summation from lambda ICI. Okay guys, so if you take now from this side and from this side, if you take nu sigma fission over sigma absorption as a common factor, you will end up with N of t sigma absorption V, and you will take what? Nu sigma what? Nu sigma fission divided by what? Sigma absorption out. This will give you what? 1 plus L square B square G multiplied by what? K effective minus 1 divided by what? Nu sigma fission over sigma absorption minus beta plus summation of lambda I Ci of t. Do you have any objections, guys?
Sigma A should cancel.
Sigma A will cancel, yes. So when sigma A will cancel, dn of t by dt equal to N of T multiplied by what? V. Somebody says that sigma A will cancel, and I will have nu sigma fission multiplied by. Guys, this guy here, I can write it as what? I can write it as 1 over 1 plus L square B square. Yes? Yes? So, if I will write it like this, I will remove it from here. Yes, guys? Yes? So what's this again? Nu sigma Fisher over sigma absorption over blah blah blah. Yes? So this is what? K effective. So this will give me what? K effective minus 1 divided by K effective, which is what? It's a property in nuclear reactor called reactivity, rho. But anyway, so this will give me what? K effective minus 1 divided by what? K effective minus beta plus what? Summation of what? Lambda I Ci from I equal to 1 to 6. Again, what's this, guys? Nu sigma fission multiplied by V. I just define it as what? 1 over gamma. Gamma was here equal to 1 over nu sigma fission V. I told you 1 over sigma fission is lambda, mean free path, and this will be what? This will be what? N of T divided by what? Divided by gamma multiplied by what? Rho minus beta plus what? Lambda I Ci of T. And this is the second equation. So what's rho? Rho is equal to what? K effective minus 1 divided by K effective, and it's called reactivity. So how many of you took the 250 in nuclear engineering 250? So you knew what's positive reactivity insertion and negative reactivity insertion and so on. So when rho is positive, what does it mean? K is always positive number. K is less than 1 or greater than 1. K1 is what? The reactor is what? Critical. So when K effective is 1, rho is equal to what? So this is a reactor critical what? Critical reactor. When rho K effective is larger than 1, our reactor is what? Supercritical. So something greater than 1 minus 1 will give you what? Positive or negative? Positive, divided by a positive number, so this is positive. So when rho is greater than 1, this is super what? Supercritical. When K effective is 0.9, less than 1, this is equal to what? Negative. Yes? 0.9 minus 1 is what? Negative 0.1. Yes? So this will be a negative value. So when rho is negative less than 0, it's sub what? Critical. And in the nuclear engineering jargon, usually if you work in a nuclear reactor, people will not say what's your K effective or whatever. They will not say this. They will say what's the activity of the reactor. Okay, guys? Okay, guys? They will say what's the reactivity. And usually the reactivity is usually, I will tell you this in a minute, when you have rho divided by beta. And beta is what? Delayed neutron fraction of the fuel that you are using. So let's assume that rho will be what? Positive or negative. So usually you will say, when you design your nuclear reactor core, you have to have positive reactivity. You have to have K greater than 1. Your reactor should be, when you design it, supercritical. Then you will insert the control rods until you make it critical, and once you run for a long enough time, your fuel inventory will reduce because of the consumption, and then K will reduce, rho will reduce. But you have to have a stock of positive reactivity. What does it mean? You have to have your K effective higher than 1 by certain amount that makes your reactor critical for, let's say, 1 or 2 years until you will do fuel reloading for the fuel again. Okay, guys? So when you do this, we want to know how high our reactivity. So the excess reactivity over the rho equal to 0, this is called excess reactivity, core excess reactivity. So if you take all your control rods out and you design your core so that you will know how high my reactivity is, so the value be above 0, how high the value is above 0, usually they do not say we have rho of 0.6. So they say, let's say rho is 0.6. So they will say 0.6 divided by, let's say, or 0.2 divided by 0.0065, which is beta. Okay, guys? And then they will say we have how many dollars of reactivity. So this is called what? Dollars of reactivity. So please do not take this to 7-Eleven and buy anything. Okay? So this is just $1 of reactivity. How many dollars of reactivity? Of course, if you go to the nuclear guy or the nuclear bank, you can always trade and say, how many cents of reactivity in $1 of reactivity? 100 cents. So we will say that our excess reactivity, the reactivity above 0, is $2. What does it mean, $2? I have rho divided by beta equal to 2. So I have 2 betas of reactivity as a reserve, as a margin. So if beta is for uranium-235, 0065, multiply this by 2, will give you 0130. So 2 beta for uranium-235 will be 0.0130, let's say. So if you have rho as a positive quantity, which is K effective minus 1 divided by K effective is equal to 0.013, you said that I have $2 of reactivity excess in my core. Okay, guys? You need excess reactivity to be able to run. Otherwise, if you design your core and you make your core rho equal to 0, your core is critical. The moment you will start pulling your control rods, your core become what? Subcritical, and you will no longer be able to run. So you have to have a reserve of reactivity. Then you have to control this reserve of reactivity using the control rods. A second important note is you have a reserve reactivity in the core. Let's say, how many beta? Let's say I have 2 beta, 3 beta, 4 betas excess reactivity. Your control rods also will have reactivity worth. But the control rod, the reactivity, is it positive or negative? Negative reactivity. So in this case, I will have also a negative reactivity for my control rods. My control rods should have more negative reactivity than the excess reactivity of the core. Otherwise, you will have a critical accident. Once you put all the controls inside the core, still you have excess reactivity, so you will have some fission going on and you will not be able to control reactor. So if you have, let's say, 4 beta as excess reactivity, you should at least have your control rods 4.5 or 5 betas. So you will have what we call shutdown margin. Shutdown margin. So the shutdown margin is defined as the negative rho or reactivity of the control rods, or the reactivity of the control rods minus the excess reactivity of the core. This is called shutdown margin. Did you understand this stuff? In USA, they define the rho in dollars. Outside, at least when I was in Argentina and Egypt, they define the reactivity in another term. If you hear it outside, it's called BCM. So maybe you will hear this somewhere outside USA. They will say how many BCM you insert inside the core. Yes?
Can you say what the shutdown margin is again?
Shutdown margin is just defined as excess reactivity how many dollars of reactivity the core has at a given time. Because at initial startup you have excess reactivity of so and so. After a couple of weeks you will decrease it until, so this is excess reactivity. Shutdown margin is defined as shut down margin is defined as rho for the contour rod minus rho excess for the core. So now guys, how many equations now we have? 2? Who said 2? Who said 2? I will pull my hair and start crying because I spent so long time defining this. We have 7 equations. 6 equations for the 6 groups and 1 equation here. And of course, because all of us are genius, so we will be able to solve it in like this without any problem. So you need to solve 7 equations, and they are coupled differential equation. Why they are coupled? Because C of I here and C of I where? Here. Yes? So you have to know what's C of I so that you will plug in C of I here and get what? N of I. And in order to solve the C of I here, you have to know what? N of I, then you have to know N of I here. So those are 7 equations, and they are simultaneously coupled differential equations. Okay guys? So we need to know tricks so that we will be able to solve those equations. Yes? We need to know how to solve those equations. So as a first guess, we will say, from our previous study of nuclear reactor physics, you remember guys, when we studied the case for a slab geometry, and we said that the solution for the slab geometry, phi of r and t, was just equal to what? Summation of what? E to the power of some t over t capital, which is the reactor period, multiplied by some cosine bn of x. Do you remember this? And then I said that this is for n1 equal to 1 to infinity. And those are the harmonics, and then we showed that you have first harmonic, second harmonic, third harmonic, and so on. and we showed that T over Tn here will die out for the larger n quickly. Yes? And then we said that only the first harmonic e to the power of T1 cosine Bx will be the solution. So we knew that the psi of r and n of t will have this function. So why we will not be able, for example, to say, okay, I can just assume that my n of t will be an exponential function of t. So this is what we will propose here. So we will propose that your n of t is some certain function. A is a constant multiplied by e to the power of st. Okay, guys? And c I of t will just be b multiplied by e to the power of st. This is a constant, this is a constant. This is not the beta I, this is not the BG, which is the geometrical buckling. So if we assume those functions, and you do take the Laplace transformation, so this would be n of t is this and c of t is this. So substitute here with n of t, substitute here with n of t and c of I of t, ci of t. If you take the Laplace transformation for the two sides, which is the function f of t e to the power of minus st dt, this is called f of s from 0 to infinity. This is the Laplace transformation. This is one of the methods to solve differential equation is to assume that you have f of t, take the Laplace transform for both sides, then you will be able to transform the differential equation to algebraic equation as a function of s, not as a function of t. So now, if you do this, you will notice that my first equation will be just for if you remember Laplace transform, if you have an integral, let's say d by dt for a function, the Laplace transform is just s multiplied by s, f of s. So if you have d by dt for f of t, this is sfs. Okay, guys, this is from the properties of Laplace transform. So dn of t by dt, the Laplace transform will be what? S multiplied by n of what? N of s equal to rho naught minus beta divided by gamma multiplied by n of s plus the summation from I equal 1 to n lambda I ci of s plus some n naught. Okay, guys? The initial number that you start with. And s multiplied by ci of s will be also beta I multiplied by n of s divided by gamma minus lambda I ci of s plus ci naught. And this is I equal to 1 and 6. So those are two algebraic equations. Yes, guys? We can say, we can pick up the n naught and c naught to be zeros at the very early beginning. Okay? So take this equation, the second one, s ci of s minus plus lambda I ci of s and this will be equal to what? Beta I n of s divided by gamma. So what's Ci? Ci of s, you will take it as a common factor. You will be left with s plus what? Lambda I. Then C of I will be this divided by what? 1 plus lambda I. So this will be beta I n of s divided by 1 plus lambda I multiplied by gamma. So if you take this, substitute it here, so we got Ci of s from the second equation. We will substitute in Ci of s in the first equation. So when you will do this, we will get what? N of s multiplied by s is equal to rho naught minus beta divided by gamma multiplied by n of s plus the summation lambda I. Ci is what? Beta I n of s divided by 1 plus lambda I multiplied by gamma. Actually it's not 1, I think it's a s. Okay guys, now from here it's easy to eliminate what? N of s with n of s with n of s, and you will end up with what? S equal to rho naught minus beta divided by what? Gamma plus the summation of lambda I beta I divided by s plus lambda I all multiplied by gamma. Now I can take this beta. What's beta? Beta is the summation of beta I. Yes? So I can say S equal to rho naught over gamma minus beta over gamma, but beta is summation of what? Beta I over what? Gamma. And I have here a summation of beta I over what?
Gamma.
Over gamma, and I'm summing over. So all what I will do is just I will unify the what? Unify the denominators. So this will be S equal to rho naught divided by gamma minus summation of beta I divided by gamma plus 1 over gamma summation of lambda I beta I S plus lambda I. And if you will sum this with this and unify the equation, this will give you rho naught over gamma minus 1 over gamma summation of beta I S divided by S plus lambda I. So this is just an equation that we can solve. Yes? Yes, guys? What's this equation? Somebody can tell me what's this equation? What's the order of this algebraic equation? Nope. You are wrong.
Transcendental.
Nope. You are wrong. Nope. It's 7-order polynomial. Why? Because this is S rho naught over gamma minus 1 over gamma. This is beta is, so we'll call it beta 1, divided by s plus lambda 1, plus beta 2s over s plus lambda 2, beta 6s divided by s plus lambda 6. To unify this, this will be some blah 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 here, divided by s to the power of 6 plus s to the power of 5a 6 plus something, because you will have the first multiplied by the second multiplied by all up to the what? Up to the 6. So if you multiply all those 6 in the denominator, will give you 6 order polynomial. Yes? Then you multiply both sides by this 6 order polynomial to get rid of it from the denominator. You will have 6 order polynomial multiplied by s. So this will give you 7th order what? Polynomial. So you have to have 7 roots. So when we will solve this equation, we expect what? 7 roots. 7 what? Root. And this will be the fun next time. Okay, guys? Do you have any questions? Yeah.
We could also take the inverse Laplace transformation, though, and get a function of time.
Yeah, but yeah. Did you have, yeah.
Didn't we neglect the C I node here in this equation?
I said that we will start with n naught c naught equal to 0.
We assume initial condition is 0.
Okay, guys? So usually when you solve this, you will get 7, those 7 roots, as we will see later. If you remember the case for the slab, all of them will die except the first one, and usually the reactor period is governed by the first root. Okay, so the first root is the slowly decaying one, okay, and it is the fastest decaying one if you have a negative reactivity. Okay, guys, it's a slow decaying one.